this is Swathi, working as Assistant Professor in Institute of Aeronautical Engineering in the Department of Electronics and Communication Engineering. Welcome to today's lecture. In this lecture, we are going to discuss the operation of full wave rectifier, basically the types of full wave rectifiers, the operation of center tap full wave rectifier, and the mathematical analysis of center tap full wave rectifier. So, full wave rectifier. What is a full wave rectifier? So basically we know that rectifier is a circuit which is used to convert an AC supply voltage into DC supply, whereas full wave rectifier is a circuit which rectifies both positive and negative half cycles of AC input voltage is called as full wave rectifier. So depending upon the construction, or else the type of construction we are using in a full wave rectifier. The full wave rectifiers are classified into two types: center tap full wave rectifier and bridge full wave rectifier. So center tap full wave rectifier we'll be discussing in this lecture. So what is center tap full wave rectifier and what are the advantages of center tap full wave rectifier? So center tap full wave rectifier is named because the secondary winding of the transformer is divided into two halves by providing a center tapping, which provides an equal voltage in the two halves of the secondary winding, but both have opposite polarity. So this center tapping is mainly used. The major drawback of half wave rectifier is it can rectify only the positive half cycle. That means the diode conducts only during the positive half cycle of the input AC supply, whereas a negative half cycle was removed. So in order to make the diode to conduct in both the half cycles, we are dividing the secondary winding into two halves by providing a center tapping and connecting two diodes, one in the upper half of the secondary winding and one in the lower half of the secondary winding. So this is a circuit which shows the center tap full wave rectifier, in which the secondary half is divided into two. Secondary winding is divided into two halves, upper half and lower half, and this is the tapping, which divides the secondary winding into two halves, and one diode is connected in the positive upper half of the secondary winding and the other diode is connected in the lower half of the secondary winding. And this structure makes that the current can flow through the load resistor during both the half cycles of AC input supply. Whereas in half wave rectifier, the current flows through the load resistor only during the positive half cycle of input, and that is the negative half cycle of input AC supply, the diode is reverse biased and hence there is no flow of current through the load resistor. So as the name itself indicating, full wave rectifier which rectifies both positive and negative half cycle, we are providing a center tapping at the secondary winding such that two diodes are connected, one in the upper half and one in the lower half, such that two diodes will be conducting and hence the current flows through the load resistor in both of the half cycles. Now let us see how the current flows through the load resistor in both the positive half cycle and negative half cycle of the input AC supply, and also how this center tap full wave rectifier can rectify both the positive and negative half cycle. We'll see. So this is a center tap full wave rectifier. So this is a transformer, primary winding and secondary winding. The type of transformer used here is step down transformer, and this secondary winding is provided with a tapping in the center, that is center tap, and two diodes are connected here, one in the upper half which is D1 and the other one is in lower half of the secondary winding, that is D2, and a load resistor is connected to the two cathodes of diodes. So diode D1 cathode and to the diode D2 cathode a resistor is connected. That means a load resistor is connected in between the cathodes of two diodes and ground. So here, while we are providing the center tapping, this center point of the secondary winding acts as a neutral point. That means it acts as a ground. So here the load resistor is connected to the cathodes of diode and the ground. Now let us analyze the operation of center tap full wave rectifier. What happens during the positive half cycle? So during the positive half cycle, so as I told you that we are dividing the secondary winding into two halves. So we will be getting equal voltage at the two halves of the secondary winding, but opposite polarity. So that is plus minus in the upper half and plus minus in the lower half. So that means during the positive half cycle, point A is at more positive potential, whereas point B of the secondary winding is at more negative potential. And hence, as a diode D1's anode is connected to point A, which is applied with more positive voltage, the diode D1 gets forward biased. And the diode D2, whose anode is connected to point B, which is at more negative potential during the positive half cycle of input supply, which makes the diode D2 reverse biased. As the diode D2 is reverse biased, it will be open circuited and hence no current flows through the diode D2 because it is open circuited. So now during the positive half cycle, diode D1 gets forward biased, which is indicated with the dark red color, and diode D2 gets reverse biased because point B is at more negative potential. So we are applying negative potential to the anode, which makes the diode D2 reverse biased and hence it is open circuited. So the diode D2 is open circuited and hence we have shown it with light color. So as it is open circuited, no current flows through the load resistor through the diode D2 because it is open circuit. Now, as the diode D1 is forward biased, now there is a flow of current which starts from point A through diode D1 and through load resistor RL and again through center tapping and again through point A. So this is the flow of current and also the direction of current flow through the load resistor. That means the current flows from load resistor from cathode to the ground, cathode of the diode to the ground. So this is the direction of current flow through the load resistor. So as the input is varying sinusoidally, because at the secondary winding, even though we are providing center tapping, it also provides sinusoidal voltage at the two halves of the secondary winding. So as the input voltage is varying sinusoidally, so the current flowing through the load resistor will also vary sinusoidally, which results in some DC output voltage across the load resistor, which also varies sinusoidally. That means the output current IL is varying sinusoidally. This is during the positive half cycle of input voltage. This is V in, okay, and this is IL. As the load current is varying sinusoidally, so the output voltage across the load resistor, which we are representing as V out, will also vary sinusoidally from 0 to pi. That is during the positive half cycle of input voltage. So this current through the load resistor is due to the diode D1, which is on during the positive half cycle of input voltage. Now, what happens during the negative half cycle? So that means reverse operation happens here. Means during the positive half cycle, point A has become positive, point B has become negative. So now during the negative half cycle, point A becomes more negative with respect to point B, and hence the diode D1, whose anode is connected to point A, which is at more negative potential, will get reverse biased and hence it is open circuited. That is why I have shown it with a light color. And as diode D2's anode is connected to point B, which is at more positive potential, makes the diode D2 forward biased and hence it is short circuited. Short circuited means it offers very less forward resistance. Okay, So that is almost equal to 0. That is almost equal to 0. So it is approximately equals to 0. The forward resistance offered by the diode which is on is 0. Approximately equals to 0. So and hence the current flows through the diode D2 through the load resistor and through the lower half of the secondary winding. So this is the flow of current. So again this is happened due to the negative half cycle of input. This is my input and this is during the negative half cycle of input. So what happens here? The current flows through the load resistor, so which will be in the same direction as that of the current flowing through the load resistor during the positive half cycle. So this is the load current. As the input is varying sinusoidally, so the load current, the current flowing through the load resistor will also vary sinusoidally, which results in a positive half cycle of output voltage across the load resistor, which is represented with Vout. Let us indicate this current as I2, whereas in the previous case, let us indicate this current as I1. During the positive half cycle, the current which is flowing through the load resistor, I am calling it as I1, whereas during the negative half cycle, the current which is flowing through the load resistor is I am representing as I2. And now the total current flowing through the load resistor during a complete half cycle of input voltage Vm sin omega t can be represented as the addition of I1 and I2. That is, the current that is flowing through the load resistor is a sum of current I1 and I2. Whereas current I1 is a current flowing through the load resistor during the positive half cycle of input, whereas I2 is a current flowing through the load resistor during the negative half cycle of input voltage. And hence IL is equals to I1 plus I2. And similarly, output voltage is also we are going to get. So that let us see why I am taking it as IL is equals to I1 plus I2, because during the positive half cycle the current is starting from point A through the diode D1 which is on and through the load resistor and through the upper half of the secondary wire, and during the negative half cycle the current starts flowing from point B through the diode D2 which is on and through the load resistor and through the lower half of the secondary wire. So in both the cases, this is during the positive half cycle and this is during the negative half cycle. In both the cases, the current through the load resistor is in the same direction. So here also the current is flowing from this to this side, and in this case also the current is flowing from this side to this side. That means the current flowing through the load resistor during both the half cycles is in the same direction. And hence IL can be considered as I1 plus I2. So that is why we are going to get two positive half cycles of current flow through the load resistor during the positive and negative half cycles of input supply. And as the load current is varying like this, the output voltage across the load resistor will also have positive half cycles during both the cycles of AC input voltage. Let us have a look at the input and output voltage, input and output waveforms of full wave rectifier. So the first one is the input waveform, which is represented mathematically as Vm sin omega t. This is nothing but Vs. Let us consider this as the input voltage Vm sin omega t. So 0 to pi it is positive, whereas pi to 2 pi it is having negative half cycle. And during the positive half cycle, diode D1 is on, which leads to a current flow through the load resistor, which is also varying sinusoidally. So let us have this one as I1. This is the flow of current through the load resistor when during the positive half cycle of input, and this is happening due to the diode D1 which is on, and in this case diode D2 is off. So next, during the negative half cycle, the current flowing through the load resistor we are representing as I2, and it is also varying sinusoidally with respect to time, and the polarity of I1 and I2 are same because this I1 and I2 are flowing in the same direction through the load resistor RL, and hence those two are considered to be positive half cycle. Those two are considered to be positive half cycles. Now the total current IL, so which I have not shown it here, so is equals to I1 plus I2, so which will have all positive half cycles. So this is 0 to pi, 2 pi, 3 pi and so on. Omega t on x-axis, and this is IL, which is equals to I1 plus I2. I1 plus I2. So which leads to only a positive half cycle of output voltage across the load resistor. So this is the output voltage across the load resistor waveform, which is representing the output voltage across the load resistor, which is having only positive half cycles of output. So next up, so as we have seen the output waveforms, now we are going for the so that means here if you observe this waveform, so we have positive half cycles. No half cycle is removed here when compared to the half wave rectifier. In half wave rectifier, we were getting zero output voltage across the load resistor. So that is a major drawback, and hence we are getting only 40.6% of efficiency. Whereas here we are able to rectify both the positive and negative half cycle of input AC supply. So now let us calculate the efficiency and all the other performance characteristics of center tap full wave rectifier. So first let us start with DC output current and DC output voltage. So always you remember DC current or DC voltage will be measured as average value, and the average value can be found out by finding the area of the curve, which is representing load current or else output voltage. So this is the output voltage output current equation, waveform, 0 to pi, pi to 2 pi, 3 pi, and here this is IM. So we can also represent this IL as IM sine omega t. IM sine omega t. So here this is happening for both 0 to pi and also for pi to 2 pi. So that is why if you find out the average value for the curve from the limits 0 to pi, it is enough because it is repeating. Okay, there is no change in the waveform for the next half cycle of input. So that is why the average value of output waveform can be found out by considering only the waveform from 0 to pi. And hence the average value, which is represented with IDC, can be obtained as 1 by pi. That means I am considering only the first cycle, 1 by pi integral 0 to pi IL d omega t. This is nothing but the average value for this waveform. As it is repeating, so I am just considering this only for the duration of 0 to pi. So now just substitute IL value here, 0 to pi, that is IM sine omega t d omega t. So now 1 by pi, so I am taking IM as constant, and which is I am taking it out of the limit, 0 to pi sine omega t d omega t. Now we already know that the integration of sine is minus cos. So Im by pi minus cos omega t, and the limits are from 0 to pi. Now just substitute the limits. Whenever we are substituting the limits, first upper limit minus lower limit. So that is Im by pi, and the upper limit minus cos pi. Cos pi is minus 1. Minus of minus, it is plus 1, minus of minus cos 0. Minus cos 0 is 1. Cos 0 is 1, and minus cos 0 means minus 1. So this is the limits. So Im by pi into 1 plus 1, so which is 2 Im by pi. So this is the value of IDC. This indicates that average value of current flowing through the load resistor, or else the DC value of output current, so which is given by 2 Im by pi, where Im is the maximum value of current flowing through the load resistor. So this is IDC. And now we'll find out VDC. So VDC is nothing but IDC into RL. So VDC is the output voltage or else DC output voltage across the load resistor. So this is calculated by taking IDC into RL. So IDC can be given by 2 Im by pi into RL. So already we know that whenever we are considering a diode resistance, that is forward resistance of the diode. This is forward resistance of the diode, which is negligible, and ideally it is equals to 0. Okay, and we are also considering the internal resistance of secondary winding. Internal resistance of secondary winding. So now, if you consider this into effect, then the value of Im can be, and if you observe the circuit, so the diode resistance that is under forward bias condition is in series with the load resistor. And the internal resistance of this secondary winding is also connected in series. That means RS, RF and RL are all connected in series, and hence same current flows through the all the components, and hence Im can be obtained as Vm by Rs plus Rf plus RL. So this is maximum current Im. So now I'm just going to substitute this in the equation, that is VDC, that is equals to 2 by pi into RL into, in place of Im I am substituting Vm by Rf plus Rs plus RL. If I consider Rf plus RL is very much less than RL, then I can neglect this. Then I will get VDC as 2 by pi into RL into Vm by, if I neglect Rs plus Rf, then I can get only RL. So RL get cancelled. So now I will get VDC as 2 Vm by pi. So this is the value of output voltage, DC output voltage across the load resistor. So DC output current across the load resistor is Im by pi, 2 into Im by pi, whereas VDC is equals to 2 Vm by pi. Now, so that is about the DC value of output voltage across the load resistor, and also the DC value of current flowing through the load resistor. Now, as we all know that the output of a rectifier contains AC components plus DC components. So what that IDC and VDC represents the DC component present in the output of the rectifier. Now we are going to find out the AC components present in the output of rectifier that can be calculated by RMS value, that is root mean square value. So we know the formula of root mean square value. So again we are finding out the root mean square value for the same waveform. So first let us consider IL waveform. So this is my IL waveform, 0 to pi, 2 pi, 3 pi, omega t, and this is IL. So now the IRMS root mean square value can be found out. So even if you find this RMS value for the one cycle, then that is enough because it is repeating. So that is why I can write the formula for that as 1 by pi integral 0 to pi, because I am considering only half cycle. So because the output is identical for both the cycles, so just I am taking one cycle and I am just finding the RMS value. 1 by pi IL square d omega t whole to the power of 1 by 2, that is root mean square value. Now substitute the value of IL square. So that is 0 to pi square, that is Im square sine square omega t d omega t whole to the power of 1 by 2. Now we already know that sine square omega t can be written as 1 minus cos 2 omega t divided by 2. This is a formula. So now I'm taking this Im square out of the integration. So Im square by pi integral 1 minus cos 2 omega t. Even I'm taking this 2 out, 2 pi d omega t, and the limits are from 0 to pi, and here we have whole to the power of 1 by 2. So now Im square divided by 2 pi. So integration of constant is equals to omega t. So omega t, and the limits are from 0 to 5, minus integration of cos is sine 2 omega t divided by 2, 0 to pi whole to the power of 1 by 2. So now Im square divided by 2 pi. So here now I am substituting upper limit minus lower limit in omega t. So pi minus 0 minus sine pi is 0 and sine 0 is also 0. Sorry, here the whole power we need to consider, whole power 1 by 2. So now Im square by 2 pi into pi we are getting. So this one get cancelled. Whole to the power of 1 by 2. Whole to the power of 1 by 2 means root. So if you apply the root, then I will get Im by root 2. So this is the value of IRMS, that is RMS value of output current across the load resistor, which represents the AC component present in the output of the rectifier. So IRMS is equals to Im by root 2. So this is IRMS value. Now similarly, we are going to find out VRMS. So VRMS is equals to IRMS into RF plus RS plus RL. So here now again IRMS value is Im by root 2. I am just substituting the IRMS value, RF plus RS plus RL, and we know that Im is equals to Vm by Rf plus Rs plus RL. So now just substitute this one in the above equation. So then VRMS is equals to Vm divided by Rf plus Rs plus RL into Rf plus Rs plus RL divided by root 2. So this one get cancelled. So VRMS value is equals to Vm by root 2. So this is the value of RMS voltage across the load resistor, which represents the AC component. So now we have calculated average value and RMS value of output voltage across the load resistor. Now the next thing is, using this average value and RMS value, we are now calculating the efficiency of the rectifier. So we already know the definition of efficiency. So for the efficient work of performance of any circuit, the efficiency should be high, and the efficiency can be defined as the ratio of DC output power delivered to the load to the AC input power from the transformer secondary. So that is, we can define efficiency, or we can represent efficiency with eta, that is given by PDC by PAC. So PDC, that is DC output power delivered to the load. So whenever DC current flows through the load resistor, then only DC output power will be delivered to the load, and hence PDC can be written as IDC square into RL. IDC square into RL. Whereas AC power can be calculated across the transformer secondary. So by considering RMS value of current flowing. So IRMS square into RF plus RS plus RL. RF plus RS plus RL. Okay. So now just substitute this in the equation. So IDC square into RL divided by IRMS square into RF plus RS plus RL. So now just substitute the value of, and before the substituting the value of IDC and IRMS, I am just considering that RF plus RS is very much less than RL, and hence I can neglect this one. So that is why I can get IDC square into RL divided by IRMS square into RL. So this one get cancelled. So now we have efficiency that is equals to IDC square divided by IRMS square. So we know the value of IDC, that is 2Im by pi whole square divided by IRMS value, we know that Im by root 2 whole square. So here Im get cancelled. So 4 by pi square divided by 1 by 2, because 1 by root 2 whole square. So now we'll get it as, if it goes to the numerator, it will be multiplied by 4. So that is 8 divided by pi square. So pi square nothing but 3.14 whole square. So if you find out the value of this one, you will get this value as 0.812. So if I want to calculate the efficiency in terms of percentage, then you will get the efficiency as 81.2%. So this is the efficiency of center tap full wave rectifier. Whereas the efficiency of half wave rectifier was 40.6%. So that this is for the half wave rectifier efficiency, right? So now if you observe this, the rectifier efficiency of full wave rectifier is just double the efficiency of half wave rectifier. That means the efficiency got improved. This is an advantage here. Why the efficiency got improved? Because in that case, one half cycle of the input was removed in case of half wave rectifier. Whereas in this circuit, it is just rectifying both positive as well as negative half cycles, and hence the efficiency got improved. So where this is considered to be an advantage of full wave rectifier. Now similarly, we are going to calculate the ripple factor. So as we all know, ripple factor is a factor which is used to find the amount of ripples present in the DC output of the rectifier. Ripples nothing but unwanted signals. So that means the unwanted signals in the rectifier is AC components. That means in the given output, what is the amount of AC component present? That can be calculated by using this ripple factor. So we can have a definition of ripple factor. It is defined as the RMS value of AC components to the average value of output voltage across the load resistor. That means VRRMS divided by VDC, where VRRMS represents the RMS value of the ripple voltage. Ripple voltage is nothing but AC voltage present in the output of DC, output of rectifier. So here VRRMS can be found out simply by subtracting average value from the RMS value. So that means if you remove the average value from the RMS value, it will give you only the AC components, which are nothing but the ripples. So that is why as I am taking RMS value, I can have the VRRMS formula as under root of VRMS square minus VDC square. After substituting this in the above equation, so by simplifying that, we are going to get the ripple factor formula as VRMS by VDC whole square minus 1. So we already know the VRMS value of half full wave rectifier, so which is Vm by root 2, and average value of output voltage, which we know that 2 Vm by pi. Just substitute these two values in the above formula. So we will be getting Vm by root 2 whole square divided by 2 Vm by pi whole square minus 1. So here this Vm and Vm square will get cancelled. Then we will be getting 1 by 2 in the numerator divided by 4 by pi square in the denominator minus 1. So it is what we are going to get, pi square divided by 8 minus 1. So if you find the value of this one, ripple factor, we are going to get the ripple factor value as 0.287. So if you find the value of this one, the ripple factor value will be 0.287. So this is the ripple factor where it got very much reduced when compared to the half wave rectifier. In case of half wave rectifier, it was 1.21. That means 121% of ripples are present in the output of DC. Whereas in this one, the ripple factor was reduced to 0.2. Actually, sorry, 0.482. 0.482. That means if you take the value, that is pi square by 8 minus 1 under root, it will give you 0.482. That means 48.2% of ripples are present in the output of full wave rectifier. So this is a ripple factor of a full wave rectifier. Now, coming to the transformer utilization factor. Transformer utilization factor is mainly used to identify how much of AC power which is generated at the transformer secondary is being converted into DC. That means while converting the AC into DC, how much of the transformer AC power rating of the transformer secondary is utilized. That is defined by the transformer utilization factor. So, and it is defined as a ratio of DC power delivered to the load to the AC rating of the transformer secondary winding. So, that is PDC by PAC rated. But here, what happens? In case of center tap full wave rectifier, we are dividing the secondary winding into two halves. That means during the positive half cycle, diode D1 conducts and it acts as a half wave rectifier. That means the upper half of the secondary winding acts as a half wave rectifier, and during the negative half cycle, as diode D2 is forward biased, the lower half of the secondary winding acts as a half wave rectifier. That means here, in case of transformer utilization factor of full wave rectifier, we cannot calculate it directly because the secondary winding has got a center tapping, and hence it is divided into two halves, which provides equal and opposite polarity voltages in the two halves of the secondary winding. And hence, the transformer utilization factor for the center tap secondary winding can be calculated by taking the average of transformer utilization factor of primary and the transformer utilization factor of secondary. Because we are dividing the secondary winding into two halves. And now, how to calculate the transformer utilization factor of primary? Let us calculate TUF of primary winding. So, as I told you that we are dividing the secondary winding into two halves. So, let us indicate this one with TUF primary. So, how can we calculate this? So, we are dividing the secondary winding into two halves, and during each half the half cycle, either upper or lower half of the secondary winding acts as a half wave rectifier, and hence the transformer utilization factor of primary winding can be obtained by just multiplying the transformer utilization factor of a half wave rectifier by 2. Okay, so because whatever the input voltage that we are getting in the primary winding is getting divided into two halves. So in each case, it is acting like a half wave rectifier. So that is why it can be obtained by transformer utilization factor of half wave rectifier. So which we already know, that is 0.287. 2 into 0.287 is equals to is 2 into 0.287 is equals to 0.574. So this is the transformer utilization factor of the primary. And coming to the transformer utilization factor of secondary winding. Transformer utilization factor of secondary winding. So which we can calculate it as directly, that is PDC divided by PAC rated. Okay, so PDC is nothing but VDC into IDC divided by PAC rated. So in case of half wave rectifier, we have got the output like this. So that is why the RMS value of this one was different from the RMS value of this one, which we are getting from the secondary winding. Okay, this is VS RMS. These were different. But in case of this, we have got the output voltage across the full wave rectifier, that is load resistor of a full wave rectifier, is this one. It is also having two cycles, either it is a positive half cycle or negative half cycle. We have two cycles. Anyhow, we are going to find out VS RMS. Okay, so that means in this case, as it is having two half cycles, whereas in the above, that is due for this is for the half wave rectifier, the negative half cycle was removed. So this VRMS was different from the VSRMS. But here in this case, as the output voltage is also having two cycles, so to which we have find out the VRMS value as Vm by root 2. This will also be equal to VSRMS. That is equals to Vm by root 2. This is the thing which I want to say. So now this can be calculated as VRMS into IRMS. So VDC value we know, that is 2 Vm by pi into 2 Im by pi divided by, and VRMS value is Vm by root 2 into Im by root 2. So Vm, Im get cancelled. So 4 by pi square divided by root 2 into root 2, it is 2. So that is 8 by pi square, whose value we have got it as 0.812. So this is nothing but TUF of secondary. TUF of secondary. And as I told you that transformer utilization factor of full wave rectifier, center tap full wave rectifier, is nothing but the average value of transformer utilization factor of primary and secondary. So that we can write it as TUF primary plus TUF secondary divided by 2, which is given by 0.574, which is the transformer utilization factor for primary winding, plus 0.812 divided by 2, which we can get it as 0.693. So this is the transformer utilization factor of center tap full wave rectifier. Okay, and here if you compare the transformer utilization factor of half wave rectifier, it was 0.287. Means what? Only 28.7% of AC power rating of the transformer secondary got utilized in order to convert the AC supply into DC, whereas it is improved from 0.287 to 0.693 in case of center tap full wave rectifier. This is transformer utilization factor. Peak inverse voltage. As we already know that the peak inverse voltage is the maximum reverse voltage that a diode can withstand without any damage. So in case of center tap full wave rectifier, as we have divided the secondary winding into two halves, we are connecting two diodes, one in the upper half and the other one in the lower half of the secondary winding, and a load resistor is connected in between the center tapping and the cathodes of the diode. So here, during the positive half cycle, so what happens? Diode D1 is forward biased. This is diode D1 and this is diode D2, and D2 is reverse biased, and hence it is open circuit. As the diode D1 is forward biased, the current flow through the load resistor is due to the diode D1, which leads to a voltage drop across the load resistor, which is equals to Vm. And here even we have a voltage drop of a voltage of Vm, which is appearing in the secondary winding, lower half of the secondary winding, and hence if you apply, as the diode D2 is reverse biased, so which is open circuited, so if you apply the KVL, so the total voltage Vm plus Vm, which is equals to 2 Vm, is going to be dropped across the diode, which is open circuited. As it is open circuited, no current flows, and hence the total voltage will be dropping across this reverse biased diode, and hence the peak inverse voltage of the diode D2 during the positive half cycle of input voltage is equals to 2V. And this same thing happens during the negative half cycle, but during the negative half cycle, this will be forward biased and this diode will be reverse biased, and now the current through the load resistor is due to diode D2, which leads to again a voltage drop of Vm, and again we have a voltage of Vm in the upper half of the secondary winding. So if you apply again a KVL, so the total voltage which is dropped across the diode with D1, which is open circuited, is also equals to Vm plus Vm, which is 2Vm. So that means the peak inverse voltage rating of the diode in case of center tap full wave rectifier is 2Vm. So it is considered to be a drawback of, that means the peak inverse voltage rating is improved, and it is considered to be a drawback. Why it is considered to be a drawback? That means the diode has to withstand for more reverse voltage applied. When we increase the reverse voltage applied to a diode, so what happens? Due to the thermal effect, more heat will be generated. In order to make the diode to withstand such a lot of heat, it should be made wider. That means the size of the diode should be increased. As the diode size is increased, the cost is also increased. So that means the high peak inverse voltage rating of the center tap full wave rectifier leads to the increase in the cost and also the size of the diode. So this is considered to be a drawback of center tap full wave rectifier. Now coming to the form factor, which is defined as a ratio of RMS value to the average value, and it is denoted by F, which is given by RMS value by average value. So it is mainly used to find out the absolute value of all the points on the waveform. So here already we know that RMS value, which is equals to Vm by root 2, and the average value is 2 Vm by pi. So Vm get cancelled. So it will become pi by 2 root 2. It will become pi by 2 root 2. So the pi by 2 root 2 and the value of this one, if you calculate, it will be equals to 1.11. So the form factor of full wave rectifier is full wave rectifier is 1.11. So which is reduced, whereas in case of half wave rectifier it was 1.57. So which also represent more amount of RMS, that means RMS value in the numerator, means that among the output of output of rectifier, we have more amount of AC components present. So it is reduced when compared to the half wave rectifier. That means the form factor is less when compared to the half wave rectifier. Now coming to the peak factor, it is defined as a ratio of peak value to the RMS value, and it is a factor which is to be considered in order to find out the peak value of the ripples present in the rectifier output. And we already know that peak value is equals to Vm, because in the output we have the maximum value as Vm. If you consider this is my output. So this is considered to be the peak value. Vm divided by RMS value is Vm by root 2. So that is Vm get cancelled. So root 2, it is 1.414. So this is a peak factor. Whereas a peak factor for half wave rectifier, it was 2. That means the peak value is reduced somewhat when compared to the half wave rectifier. So this is also considered to be an advantage of center tap full wave rectifier. So these are all the factors that are to be calculated or else considered when we are analyzing the performance of a rectifier. Now let us discuss the advantages and disadvantages of full wave rectifier. So as we have observed the mathematical analysis and operation of center tap rectifier, we can have the advantages such as efficiency is higher, which is equals to 81.2%, which is just double the half wave rectifier efficiency of half wave rectifier, and large DC output power, and also ripple factor is less, where the ripple factor is 0.482, where it was 1.21 for half wave rectifier. It is considered, these are the advantages here, and even you can include few more advantages. Transformer utilization factor is high, which is equals to 0.693, and even form factor is less when compared to the half wave rectifier. Form factor less, and peak factor is also less. Peak factor is also less. So already we have calculated this is 1.11, whereas this is 1.414. So these are all the advantages of full wave rectifier. Now coming to the disadvantages. So as we have seen, center tapping in the secondary winding, the cost of the center tap transformer is high. So providing a tapping in the secondary winding is costlier. That means center tap transformer is costlier. And when compared to the complexity, circuit complexity, when compared to the half wave rectifier, this full wave rectifier is somewhat complex. And the major disadvantages or disadvantage of this full wave rectifier is peak inverse voltage rating of the diode is higher, which increases the size and also cost of the diode. And here the cost is also more, because when compared to the half wave rectifier, the cost is also more, as we are providing a center tapping and number of diodes required are 2. So that is about the advantages and disadvantages of full wave rectifier. I hope it is clear to everyone. That's all for today. Thank you, Vanenda.
Like, share and subscribe. Hit the bell icon for more updates.